Welcome to Chapter 4, where we'll explore one of the most versatile and widely used non-destructive testing methods, electromagnetic testing, commonly abbreviated as ET. In this chapter, we'll study three important electromagnetic inspection techniques: eddy current testing, alternating current field measurement, or ACFM, and remote field testing, known as RFT. Although all three methods are based on the principles of electromagnetism, each has unique operating characteristics, inspection capabilities, and industrial applications. Electromagnetic testing is specifically designed for inspecting electrically conductive materials without causing any damage to the component. Unlike methods such as liquid penetrant testing or magnetic particle testing, ET relies on the interaction between magnetic fields and induced electrical currents to detect flaws, evaluate material properties, and measure changes in thickness. Among these techniques, eddy current testing is by far the most widely used in industries such as aerospace, power generation, petrochemical plants, manufacturing, and heat exchanger inspection. Its ability to rapidly detect surface and near-surface discontinuities without direct contact makes it an invaluable inspection tool. As we progress through this chapter, you'll first develop a solid understanding of the fundamental electromagnetic principles that make these inspection methods possible. We'll then examine how eddy currents are generated, how they interact with conductive materials, and how inspectors interpret changes in electrical signals to identify defects. You'll also learn about probe types, instrument configurations, inspection parameters, advantages, limitations, and practical industrial applications. Whether you're preparing for ASNT Level II or Level III certification, or working in the field, mastering these concepts is essential for performing reliable electromagnetic inspections. By the end of this chapter, you'll understand not only how electromagnetic testing works, but also why it has become one of the fastest, cleanest, and most effective NDT methods for inspecting conductive materials. Now that we have an overview of the chapter, let's begin by understanding what electromagnetic testing is and explore the three primary techniques used throughout the industry. Before we begin exploring the technical details of electromagnetic testing, it's important to understand the learning journey we'll follow throughout this chapter. Think of this roadmap as an overview of the major concepts that we'll build upon step by step. The chapter is organized into 4 logical sections, with each section laying the foundation for the next. By the end of the chapter, you'll have a complete understanding of how electromagnetic testing works, how it is applied in industry, and how inspection results are interpreted. Let's begin with the first section, electromagnetic testing techniques. Here, we'll introduce the 3 primary methods within the electromagnetic testing family: eddy current testing, alternating current field measurement, commonly known as ACFM, and remote field testing, or RFT. Although all 3 methods are based on electromagnetic principles, they differ in operating frequency, probe design, signal analysis, and inspection applications. Since eddy current testing accounts for the majority of industrial electromagnetic inspections, it will receive the greatest emphasis throughout this chapter. The second section focuses on basic principles and theory. Before anyone can confidently perform eddy current inspections, they must understand the science behind them. We'll study the pioneering work of scientists such as Hans Christian Oersted, Michael Faraday, Heinrich Lenz, and James Clerk Maxwell, whose discoveries established the relationship between electricity and magnetism. You'll learn how electromagnetic induction generates eddy currents, and why these currents form the basis of modern electromagnetic inspection. The third section examines the properties of eddy currents. We'll explore how eddy currents behave once they are induced into a conductive material. Important topics include the depth of penetration, the influence of electrical conductivity and magnetic permeability, and how these factors affect signal response. We'll also explain impedance changes and how inspectors use these changes to identify cracks, corrosion, material thinning, and other discontinuities. Finally, the fourth section covers applications and inspection parameters. This is where theory is translated into practical inspection. We'll discuss where eddy current testing is commonly used, how to select the appropriate probe for different components, and how inspection parameters such as frequency, gain, filtering, and standardization are adjusted to achieve accurate and reliable results. You'll also learn about the advantages and limitations of the method, helping you understand when electromagnetic testing is the best choice and when another NDT technique may be more appropriate. By following this structured approach, from basic concepts to real-world applications, you'll develop both the theoretical knowledge and practical understanding needed to perform electromagnetic inspections with confidence. Now that we've reviewed the chapter roadmap, let's begin by answering the most fundamental question. What is electromagnetic testing, and why has it become one of the most widely used non-destructive testing methods in modern industry? Now that we've seen the roadmap for this chapter, let's begin by understanding what electromagnetic testing actually is and why it plays such an important role in modern non-destructive testing. Electromagnetic testing, or ET, is a family of NDT methods used to inspect electrically conductive materials without damaging the component. Instead of using sound waves or radiation, ET relies on electromagnetic induction to detect discontinuities, evaluate material properties, and measure wall thickness or material changes. One important point to remember is that ET is only applicable to conductive materials, such as steel, stainless steel, aluminum, copper, brass, and titanium. Since non-conductive materials cannot support induced electrical currents, this method is not suitable for plastics, ceramics, or composites. The slide introduces the three primary electromagnetic testing techniques. The first and most widely used is eddy current testing, or ECT. In this method, an alternating current flowing through a probe coil creates a changing magnetic field. When the probe is brought close to a conductive material, circulating electrical currents, called eddy currents, are induced within the material. Any crack, corrosion, thickness variation, or change in material properties disrupts these currents, producing a measurable change in the instrument signal. This makes ECT ideal for detecting surface and near-surface defects. The second technique is alternating current field measurement, commonly known as ACFM. Unlike conventional eddy current testing, ACFM induces a uniform current across the surface and measures changes in the magnetic field created by surface-breaking cracks. One of its biggest advantages is its ability to detect and size fatigue cracks without requiring extensive surface preparation, making it particularly useful for offshore structures, welded joints, and in-service inspections. The third technique is remote field testing, or RFT. This method uses low-frequency electromagnetic fields to inspect thick-walled ferromagnetic tubes, such as those found in boilers and heat exchangers. A major advantage of RFT is its ability to detect defects on both the inner and outer surfaces of the tube with nearly equal sensitivity. Notice the photograph shown on the slide. It illustrates an inspector using an eddy current probe to examine a turbine rotor. Components like turbine shafts operate under high cyclic stresses, making them susceptible to fatigue cracking. Detecting these defects early prevents catastrophic failures, minimizes downtime, and improves equipment reliability. The field note also highlights one of the major industrial benefits of eddy current testing. Since no liquid chemicals or consumables are required, inspections are fast, clean, environmentally friendly, and can often be performed with minimal interruption to operations. As we continue, we'll move beyond the applications and begin exploring the scientific principles that make electromagnetic testing possible by examining the pioneering discoveries that laid the foundation for this technology. Every modern engineering technology has its pioneers, and electromagnetic testing is no exception. The inspection methods we use today are built upon discoveries made over 2 centuries by some of the greatest physicists in history. The first scientist introduced on this slide is Hans Christian Oersted. In 1820, he discovered that an electric current flowing through a conductor produces a magnetic field around it. This groundbreaking observation established the direct relationship between electricity and magnetism, and became the foundation for many electromagnetic technologies, including magnetic particle testing and eddy current testing. Next is Michael Faraday, whose work revolutionized electrical engineering. Faraday demonstrated that a changing magnetic field can induce an electric current in a nearby conductor. This phenomenon is known as electromagnetic induction, and it is the fundamental principle behind eddy current testing. Without Faraday's discovery, modern electromagnetic inspection would not exist. The third scientist is Heinrich Lenz, who explained the direction of induced currents. His famous Lenz's law states that an induced current always flows in a direction that opposes the change that created it. This opposing magnetic field is exactly what eddy current instruments detect during an inspection. Finally, we have James Clerk Maxwell, who unified the theories of electricity and magnetism into a complete mathematical framework known as Maxwell's equations. His work provided the theoretical foundation that engineers still use today to design electromagnetic equipment, antennas, transformers, and inspection instruments. The final section of the slide emphasizes that while these scientific principles have remained unchanged, inspection technology has advanced dramatically. Improvements in electronics, microprocessors, probe design, digital signal processing, and software now allow inspectors to detect extremely small discontinuities with greater speed and accuracy than ever before. For certification examinations, remember the contributions of these scientists. Questions frequently ask which scientist discovered electromagnetic induction, or which law explains why the secondary magnetic field opposes the primary field. Now that we've met the pioneers who established the science of electromagnetism, we're ready to examine exactly how eddy currents are generated inside a conductive material. This slide introduces the fundamental operating principle of electromagnetic testing, electromagnetic induction. When an alternating current flows through a coil, it continuously changes direction. As a result, the magnetic field surrounding the coil also expands and collapses repeatedly. This changing magnetic field is called the primary magnetic field. When the energized probe is placed close to a conductive material, the changing magnetic field penetrates the surface and induces circulating electrical currents within the material. These circulating currents are called eddy currents because they resemble the swirling motion of water in a river. These eddy currents do not flow randomly. They form closed circular paths that are strongest at the surface and gradually decrease in strength with increasing depth due to the skin effect. As eddy currents circulate, they generate their own magnetic field, called the secondary magnetic field. According to Lenz's law, this secondary field always opposes the primary magnetic field that created it. The inspection instrument continuously monitors the interaction between these two magnetic fields. If the material is free from defects, the current flow remains relatively uniform. However, if a crack, corrosion pit, inclusion, or thickness variation interrupts the current path, the balance between the primary and secondary fields changes. These changes appear as measurable variations in impedance, amplitude, or phase on the instrument display. The slide also briefly introduces the operating principles of ACFM and remote field testing. ACFM intentionally keeps current concentrated near the surface using the skin effect, making it highly effective for detecting and sizing surface-breaking fatigue cracks. In contrast, remote field testing uses low-frequency excitation that allows the magnetic field to travel through the tube wall, enabling inspection of thick ferromagnetic tubing. Understanding the relationship between the primary field, induced eddy currents, and the secondary field is essential because every eddy current instrument ultimately measures the interaction between these electromagnetic fields. With this foundation established, we can now examine the complete four-step induction sequence used in eddy current testing. This slide summarizes the complete sequence of electromagnetic induction in 4 logical steps. First, an alternating current flows through the inspection coil. Second, this alternating current generates the primary magnetic field around the coil. Third, when the magnetic field reaches a conductive material, it induces circulating eddy currents within the component. Finally, these eddy currents create their own secondary magnetic field that opposes the primary magnetic field. This sequence always occurs in the same order. A common certification exam mistake is reversing the last 2 steps. Remember that the eddy currents must be induced first before they can generate their own opposing magnetic field. In practice, every eddy current inspection follows this sequence, regardless of the probe type or instrument being used. Understanding this process helps inspectors interpret signals correctly and troubleshoot inspection problems effectively. Now that we understand how the electromagnetic fields are created, let's see how the inspection instrument converts these interactions into measurable electrical signals. Now that we understand how eddy currents are generated, let's examine how an eddy current instrument detects changes within a test material. The key concept is impedance, which forms the basis of signal interpretation in electromagnetic testing. Impedance is the total opposition to the flow of alternating current, or AC. Unlike direct current, where resistance is the primary opposition, alternating current experiences both electrical resistance and inductive reactance. Together, these 2 components determine the impedance of the inspection coil. Whenever the probe approaches a conductive component, the induced eddy currents create a secondary magnetic field. This field interacts with the coil's primary magnetic field, causing the coil's impedance to change. The instrument continuously monitors these changes and converts them into signals that the inspector can analyze. The slide divides the influencing factors into 2 categories: part factors and system factors. Let's begin with the part factors. Electrical conductivity determines how easily current flows through the material. Materials with higher conductivity produce stronger eddy currents and a more pronounced signal response. Magnetic permeability affects how easily magnetic flux travels through the material. Ferromagnetic materials, such as carbon steel, have high permeability, significantly influencing impedance and reducing inspection depth. Mass refers to the amount of material beneath the probe. Variations in wall thickness or metal loss alter the eddy current path and produce measurable impedance changes. Finally, homogeneity describes the uniformity of the material. Changes in microstructure, heat treatment, or composition can also influence the signal, even when no crack is present. Now let's look at the system factors. The most important is frequency. Higher frequencies increase surface sensitivity but reduce penetration depth, while lower frequencies allow the magnetic field to penetrate deeper into the material. Another important factor is magnetic coupling, often influenced by liftoff and fill factor. Liftoff is the distance between the probe and the test surface. Even a small change in this distance can significantly affect the signal. Fill factor describes how well a probe fits around or inside the component. Better coupling results in stronger and more stable signals. Field strength and the size and shape of the inspection coil also influence the sensitivity and inspection coverage. The slide also introduces the bridge circuit, which is used to detect very small impedance changes. During calibration, the circuit is balanced using either a reference coil or a variable resistor. When the probe scans sound material, the circuit remains balanced. However, if a discontinuity or material variation changes the coil impedance, the bridge becomes unbalanced. This imbalance is detected by the instrument and displayed as an inspection signal. Modern instruments can present these signals in several ways, including calibrated meters, alarms, automated sorting systems, and most commonly, the impedance plane display. This display allows inspectors to evaluate both signal amplitude and phase, helping distinguish defects from normal material variations. A common mistake among new inspectors is assuming that every impedance change indicates a defect. In reality, liftoff, geometry changes, temperature, and material variations can all produce similar responses. That's why proper calibration and signal interpretation are essential. Now that we understand how the instrument detects changes in impedance, we'll examine how eddy currents behave beneath the surface and how deeply they penetrate into a material. One of the most important characteristics of eddy currents is that they do not penetrate uniformly throughout a material. Instead, they are strongest at the surface and gradually decrease in strength as they move deeper into the component. This phenomenon is known as the skin effect. Imagine dropping a stone into calm water. The ripples are strongest where the stone enters the water and gradually weaken as they spread outward. Eddy currents behave in a similar manner, except they decay beneath the material surface rather than across the surface. The slide identifies two important penetration depths. The first is the standard depth of penetration, where the eddy current intensity has decreased to approximately 37%, or 1/E, of its original surface value. This is a standard engineering reference used in electromagnetic testing. The second is the effective depth of penetration, where the current strength has fallen to approximately 5% of its surface value. Beyond this depth, the eddy currents contribute very little to defect detection. The graphically decreasing current intensity explains why eddy current testing is exceptionally sensitive to surface breaking and near-surface discontinuities, but is generally not suitable for detecting deep internal defects. Three factors primarily control penetration depth. Increasing the inspection frequency decreases penetration, but improves surface sensitivity. Increasing electrical conductivity also reduces penetration, because stronger eddy currents are produced closer to the surface. Likewise, increasing magnetic permeability, particularly in ferromagnetic materials, concentrates the currents near the surface and further limits penetration. Selecting the correct inspection frequency is therefore one of the most important decisions an inspector makes. If the frequency is too high, deeper flaws may not be detected. If it is too low, sensitivity to small surface cracks may decrease. Understanding these principles allows inspectors to optimize inspection settings based on the material, component thickness, and expected defect type. Next, we'll explore how different material properties and component geometry influence eddy current behavior and inspection signals. Although eddy current testing follows the same physical principles, the inspection response varies significantly depending on the material being examined and the geometry of the component. Let's begin with material properties. A material with high electrical conductivity, such as aluminum or copper, allows stronger eddy currents to develop. These stronger currents generate a more pronounced secondary magnetic field, improving sensitivity. However, because of the skin effect, the current remains concentrated near the surface, reducing penetration depth. Conversely, materials with lower conductivity produce weaker eddy currents, but those currents penetrate deeper into the component. Magnetic permeability also plays an important role. Ferromagnetic materials, such as carbon steel, have high permeability, causing magnetic fields to remain near the surface. As a result, conventional eddy current testing is generally limited to surface and near-surface inspection on these materials. Now let's consider component geometry. Thin materials present a unique challenge. If the effective depth of penetration exceeds the material thickness, the magnetic field reaches the opposite surface and may create misleading signals. Increasing the inspection frequency helps confine the eddy currents within the material thickness. Another common phenomenon is the edge effect. Near edges, holes, or abrupt geometry changes, the eddy currents are forced into a smaller area, changing the coil impedance even when no defect exists. Without proper interpretation, these responses can easily be mistaken for cracks. Among all inspection parameters, frequency is the one the inspector directly controls. Adjusting frequency allows the inspection to balance penetration depth against surface sensitivity. Finally, the slide introduces phase lag. As the depth of a crack increases, the eddy current response becomes delayed relative to the excitation signal. This delay appears as a phase shift on the impedance display and helps inspectors estimate defect depth in addition to defect presence. Recognizing how material properties and geometry influence signals is essential for distinguishing genuine discontinuities from normal electromagnetic responses. Now that we understand these influencing factors, let's examine where eddy current testing is applied throughout industry.
Eddy current testing has become one of the most versatile inspection methods because it can detect defects, evaluate material properties, and measure dimensional changes without damaging the component. The primary application is discontinuity detection. Surface cracks, fatigue cracks, seams, laps, inclusions, gouges, and other near-surface defects interrupt the flow of eddy currents, creating measurable changes in the inspection signal. The photograph on this slide illustrates one of the most common aerospace applications, fastener hole inspection. Fastener holes are natural stress concentrators and are particularly susceptible to fatigue cracking due to repeated loading during service. Specialized rotating probes can inspect these areas quickly and accurately without disassembling large portions of the structure. Beyond crack detection, eddy current testing can identify material property changes. Variations in electrical conductivity or magnetic permeability may indicate differences in alloy composition, heat treatment, or hardness. The technique is also effective for identifying localized overheating. Excessive heat can alter the microstructure of a material, changing its conductivity. These changes produce measurable signal variations that may indicate thermal damage before visible signs appear. Another important application is geometry and wall thickness measurement. Corrosion on the back surface of a component reduces material thickness and changes the eddy current path. This makes eddy current testing particularly valuable for detecting hidden corrosion beneath aircraft skins, storage tanks, and heat exchanger tubing. Industries that rely heavily on eddy current testing include aerospace, petrochemical plants, power generation, manufacturing, railway maintenance, and automotive production. The method's speed, accuracy, and ability to inspect without removing protective coatings make it an indispensable tool for preventive maintenance and quality assurance.
Like every non-destructive testing method, eddy current testing has both significant advantages and important limitations. Understanding these strengths and weaknesses helps inspectors select the most appropriate inspection technique for a particular application. One of its greatest advantages is inspection speed. Large numbers of components can often be examined quickly, making the method ideal for production environments and routine maintenance inspections. Another advantage is that no hazardous chemicals or consumables are required. Unlike liquid penetrant testing, there are no developers or cleaners to dispose of, making eddy current testing cleaner and more environmentally friendly. Operator safety is also improved because the method does not use ionizing radiation or high-energy sources. In most situations, inspectors can perform examinations with minimal health risks. Perhaps the greatest technical advantage is its excellent sensitivity to small surface and near-surface discontinuities. Tiny fatigue cracks that may be difficult to detect visually can often be identified at an early stage using properly calibrated eddy current equipment. However, the method also has limitations. The inspection area covered by a probe is relatively small, meaning large surfaces require systematic scanning. In addition, eddy current testing is generally limited to surface and near-surface inspection, particularly when examining ferromagnetic materials where penetration depth is restricted. Finally, successful eddy current inspection requires a high level of operator knowledge and experience. Signal interpretation is influenced by material properties, geometry, liftoff, probe orientation, and inspection settings. Without proper training and calibration, false calls or missed indications can occur. The most effective inspectors understand not only how to operate the equipment, but also how to interpret the electromagnetic behavior behind every signal. Now that we've evaluated the capabilities of the method, we'll move on to the different types of probes and coils used to perform eddy current inspections in various industrial applications.
Now that we've explored the advantages and limitations of eddy current testing, let's discuss one of the most important aspects of a successful inspection, the selection of the correct probe or sensing element. The probe is the interface between the inspection instrument and the test object. Its design determines how the magnetic field is introduced into the material, how eddy currents are generated, and ultimately, what type of discontinuities can be detected. Choosing the wrong probe can significantly reduce inspection sensitivity or even prevent defects from being detected. The first type shown on this slide is the surface probe. Surface probes are designed to inspect flat or gently curved components, such as plates, sheets, aircraft skins, and structural members. They are among the most commonly used probes in the aerospace industry because they can accurately detect fatigue cracks around rivets, fastener holes, lap joints, and welded areas. Since the probe is scanned directly across the surface, maintaining consistent contact and minimizing liftoff are essential for obtaining stable and reliable signals. The second type is the encircling coil. As the name suggests, this coil completely surrounds the component being inspected. It is commonly used during manufacturing to inspect rods, wires, bars, and tubes as they move through automated production lines. Because the entire circumference is inspected simultaneously, encircling coils provide fast, continuous inspection and are ideal for detecting longitudinal defects such as seams, laps, and surface cracks. The third type is the inside coil, also known as an internal probe. These probes are inserted into the inside diameter of tubes and pipes to inspect internal surfaces. They are extensively used in petrochemical plants, refineries, power stations, and nuclear facilities to examine heat exchanger tubes, condenser tubes, and boiler tubing. Internal probes are highly effective for detecting corrosion, erosion, pitting, and cracking from inside the tube without requiring destructive examination. The slide also highlights several factors that influence probe selection. The first is the type of component and the surface area to be inspected. Large flat surfaces require different probes than small diameter tubing or complex geometries. The second factor is inspection speed. Automated production environments often require encircling coils for continuous inspection, while detailed maintenance inspections may require handheld surface probes. Another consideration is the inspection area. A large inspection zone may benefit from array probes, whereas localized defect detection often requires smaller, highly focused probes. Finally, inspectors must consider the expected location of discontinuities. Defects near edges, corners, or holes may require specialized probes to minimize edge effects and improve sensitivity. A common mistake made by inexperienced inspectors is assuming that increasing instrument sensitivity can compensate for using the wrong probe. In reality, proper probe selection is often more important than increasing gain, because the sensing element determines how effectively eddy currents are generated within the component. Professional inspectors always select the probe based on the component geometry, material type, expected discontinuity, location, and inspection objective before beginning any examination. Now that we've discussed the various probe designs, let's examine how these probes operate within different instrument configurations and inspection modes. Selecting the correct probe is only one part of an effective eddy current inspection. Equally important is choosing the appropriate instrument operating mode. Different inspection situations require different coil arrangements, each offering unique advantages depending on the application. The first operating mode is the absolute mode. In this configuration, a single coil performs two functions. It generates the primary magnetic field and simultaneously detects changes in the secondary magnetic field produced by the eddy currents. Since the same coil both excites and senses the response, the instrument measures the electromagnetic condition directly beneath the probe. Absolute mode is commonly used for measuring wall thickness, detecting corrosion, and evaluating gradual changes in material properties. The second mode is differential mode. Here, two or more coils are connected so that they compare adjacent areas of the test component. When both coils are positioned over sound material, their signals balance each other and little or no output is produced. However, when one coil passes over a discontinuity while the other remains over sound material, the imbalance creates a strong indication. This operating mode is particularly effective for detecting localized cracks and small defects while minimizing the effects of gradual geometry changes and temperature variations. The third configuration is the hybrid or reflection mode. In this arrangement, one coil acts as the driver to generate the magnetic field, while one or more separate pickup coils detect the response. Separating the transmitting and receiving functions improves sensitivity in many specialized applications and provides greater flexibility when inspecting complex components. The slide also introduces array probes. Instead of using a single sensing coil, array probes contain multiple coils arranged in carefully designed patterns. Electronic multiplexing activates these coils sequentially, allowing inspectors to scan large areas much faster than conventional probes while maintaining excellent coverage and sensitivity. Array technology has become increasingly popular in aerospace, railway, and manufacturing industries because it significantly reduces inspection time. Finally, the slide mentions Hall effect sensors. Unlike traditional eddy current probes, Hall effect sensors measure magnetic flux density directly and are widely used in magnetic flux leakage testing. They operate at lower frequencies and are particularly useful for detecting metal loss and corrosion in ferromagnetic materials. Each operating mode offers distinct advantages, and experienced inspectors select the configuration that best matches the inspection objective, component geometry, and expected discontinuity type. Having learned how inspection instruments operate, We can now explore the various types of discontinuities that eddy current testing is capable of detecting throughout manufacturing and service life. One of the greatest strengths of eddy current testing is its ability to detect a wide variety of discontinuities throughout the entire life cycle of a component, from manufacturing through long-term service. This slide divides these discontinuities into two major categories: manufacturing defects and in-service discontinuities. Let's begin with manufacturing-related defects. During rolling, forging, extrusion, machining, and welding processes, imperfections may be introduced into the material. Examples include forging laps, where metal folds over without fully bonding, and seams, which are longitudinal surface defects commonly found in rolled products. The slide also lists inclusions, sometimes called stringers. These are non-metallic materials trapped within the metal during manufacturing. Although they may not always be visible, they can significantly reduce mechanical strength. Other manufacturing defects include mandrel drag, hydraulic tubing flaws, surface shrinkage cracks, tubing cracks, and welding defects, including arc strikes. Each of these discontinuities disrupts the flow of eddy currents, producing characteristic signal responses that trained inspectors can recognize. The second category includes in-service discontinuities that develop after the component has been placed into operation. Among the most common are fatigue cracks caused by repeated cyclic loading. These are frequently encountered in aircraft structures, rotating equipment, bridges, and pressure-containing components. The slide also lists stress corrosion cracking, which develops when tensile stress combines with a corrosive environment, and intergranular corrosion cracking, where corrosion progresses along grain boundaries due to metallurgical changes. Finally, thread cracks often develop in bolts, threaded fasteners, and pressure-retaining components subjected to repeated loading. Understanding whether a discontinuity originated during manufacturing or developed during service helps inspectors identify the root cause of failure and recommend appropriate corrective actions. One important point to remember is that eddy current testing is most effective for detecting surface and near-surface discontinuities. Deep internal defects generally require ultrasonic or radiographic examination. Now that we know what types of discontinuities can be detected, let's examine how inspectors configure the instrument to achieve reliable and repeatable inspection results. A successful eddy current inspection depends not only on the equipment, but also on selecting the correct inspection parameters. Even the best instrument cannot produce reliable results if it is configured incorrectly. The first, and perhaps most important parameter, is frequency. As we discussed earlier, frequency controls the depth of penetration. Higher frequencies concentrate eddy currents near the surface, providing excellent sensitivity to small surface cracks. Lower frequencies allow deeper penetration and are preferred when inspecting thicker materials or searching for subsurface indications. The second parameter is coil drive. Coil drive controls the strength of the alternating magnetic field generated by the probe. Increasing the coil drive strengthens the magnetic field and improves signal strength, but it does not increase penetration depth. This is a common misconception among new inspectors. Next is gain. Gain simply amplifies the electrical signal displayed by the instrument. It is important to understand that gain increases both useful signals and background noise equally. Excessive gain may make interpretation more difficult by amplifying unwanted electrical interference. The slide also mentions display sensitivity, which adjusts how signal responses are presented on the screen. By optimizing vertical and horizontal sensitivity, inspectors can more clearly distinguish meaningful indications from normal signal variations. Another critical step is standardization, often referred to as calibration. Before any inspection begins, the instrument must be standardized using a reference standard containing known discontinuities. This ensures that signal amplitude and phase correspond to defects of known size and location. Without proper standardization, inspection results cannot be considered reliable or repeatable. The final parameters include filtering and thresholds. High-pass and low-pass filters remove unwanted signal components and improve the signal-to-noise ratio. Thresholds, sometimes called gates, automatically alert the inspector whenever a signal exceeds predetermined amplitude or phase limits. A common field mistake is changing multiple parameters simultaneously while troubleshooting an inspection. Professional inspectors adjust one parameter at a time and observe its effect before making additional changes. This systematic approach prevents confusion and improves repeatability. Proper parameter selection is one of the defining characteristics of a skilled eddy current inspector and directly influences inspection accuracy. Now that the inspection has been configured correctly, our next step is learning how to interpret the signals produced by the instrument. Once the inspection has been performed, the final and perhaps most important task is interpreting the instrument response correctly. Early eddy current instruments displayed results using simple analog meters. As the probe encountered a discontinuity, the meter needle deflected, providing only limited information about the signal. Modern instruments are far more sophisticated. Most use digital impedance plane displays, where the signal is represented as a moving point or vector. This display provides two critical pieces of information simultaneously: amplitude and phase. Amplitude indicates the magnitude of the electromagnetic disturbance. Larger discontinuities generally produce larger signal amplitudes, although geometry and material properties must also be considered. Phase provides additional information about the nature and depth of the indication. As discussed earlier, deeper discontinuities often produce greater phase shifts. By analyzing both amplitude and phase together, inspectors can distinguish cracks from liftoff, geometry changes, or material variations. The slide emphasizes an important principle. Amplitude tells you that something has changed, while phase helps explain what that change represents. Experienced inspectors always evaluate both parameters together rather than relying on amplitude alone. Modern instruments also offer numerous display and output formats, including numerical readouts, impedance plane displays, automated alarms, data recording systems, marking devices, sorting gates, and automated production controls. These capabilities enable rapid inspection while maintaining excellent traceability and quality assurance. The figure shown on the slide illustrates a modern digital impedance plane instrument. Although the display may appear complex initially, it provides inspectors with a comprehensive view of the electromagnetic response, allowing accurate characterization of discontinuities. Mastering signal interpretation requires practice, experience, and proper calibration, but it is one of the most valuable skills an eddy current inspector can develop. Now that we've covered the complete inspection process, from probe selection to signal interpretation, we're ready to summarize the key concepts learned throughout this chapter. Before moving on to the chapter review, let's summarize the key concepts that form the foundation of electromagnetic testing. This slide serves as a quick revision of everything we've covered. We began by learning that electromagnetic testing, or ET, is a family of non-destructive testing methods that uses electromagnetic energy to evaluate the condition of electrically conductive materials without causing damage. Among the available techniques, eddy current testing is the most widely used because it provides rapid detection of surface and near-surface discontinuities while requiring no couplant or hazardous chemicals. We also introduced alternating current field measurement, or ACFM, which measures changes in magnetic flux density to detect and size surface-breaking cracks, particularly in welded structures. Another important technique is remote field testing, or RFT, which operates at lower frequencies and is capable of inspecting both the inner and outer walls of ferromagnetic tubes with nearly equal sensitivity. Next, we examined how eddy currents behave. These currents flow in circular paths that are perpendicular to the magnetic field generated by the inspection coil. Their strength is greatest at the material surface and decreases with depth due to the skin effect. One of the most important concepts to remember is the four-step induction sequence. Alternating current flows through the coil, creating a primary magnetic field. This field induces eddy currents in the conductive material, and those eddy currents then generate their own secondary magnetic field that opposes the primary field. We also learned that changes in conductivity, permeability, mass, and homogeneity influence coil impedance and therefore affect the inspection signal. Finally, we discussed the importance of frequency. It is the primary inspection parameter used to control penetration depth. Increasing frequency improves sensitivity to surface defects but reduces penetration, while decreasing frequency allows inspection deeper into the material. In summary, eddy current testing is fast, safe, highly sensitive, and extremely effective for surface and near-surface inspections. However, its success depends on proper probe selection, correct instrument setup, careful calibration, and accurate signal interpretation. With these key principles in mind, let's test our understanding through a series of review questions.
Now it's time to evaluate your understanding with a short knowledge check. These questions reinforce some of the most important concepts discussed throughout the chapter and are similar in style to certification examination questions. The first question asks, which electromagnetic testing technique is most commonly used in industry? The answer is eddy current testing. Its speed, cleanliness, sensitivity, and ability to produce immediate results make it the preferred electromagnetic inspection method across industries such as aerospace, petrochemical, manufacturing, and power generation. The next question asks, where are the primary and secondary magnetic fields generated? Remember that the primary magnetic field is generated by the inspection coil when alternating current flows through it. The secondary magnetic field is produced by the eddy currents induced within the conductive test specimen. Keeping these two fields distinct is essential for understanding electromagnetic induction. The third question asks, what factors cause impedance changes in a part? The correct answer is conductivity, permeability, mass, and homogeneity. Changes in any of these properties alter the flow of eddy currents and therefore change the impedance measured by the inspection instrument. The final question asks, what shape are eddy currents, and where are they strongest? Eddy currents circulate in closed cyclonic paths and are strongest at the surface of the material. Their intensity decreases exponentially with depth due to the skin effect. When preparing for examinations such as ASNT Level II or Level III, don't simply memorize these answers. Instead, understand the principles behind them. Certification examinations often test your ability to apply these concepts in practical inspection scenarios rather than recalling isolated facts. Now that you've reviewed the key concepts, let's challenge your understanding with a more comprehensive self-test. This slide presents a series of review questions designed to help you evaluate how well you've understood the chapter. Rather than immediately looking for the answers, pause the video after each question and try to answer it yourself. This active learning approach greatly improves long-term retention. The first question asks how the depth of penetration changes in a conductive material. Recall that increasing frequency, conductivity, or permeability all reduce penetration depth because of the skin effect. The second question asks which inspection condition may affect both conductivity and permeability. Think back to our discussion on material properties and how changes caused by service conditions can influence electromagnetic behavior. The third question asks which component of the test equipment creates the changing magnetic field. Remember that it is the inspection coil, energized by alternating current, that generates the primary magnetic field. The fourth question asks for the definition of the circular electrical currents induced in a conductor by a changing magnetic field. These are, of course, eddy currents, the fundamental operating principle behind this inspection method. The fifth question asks what relationship exists between the secondary magnetic field and the primary magnetic field. According to Lenz's law, the secondary field always opposes the primary field that created it. The sixth question reviews the standard depth of penetration. You should remember that this occurs when eddy current intensity has decreased to approximately 37% of its surface value. Finally, the seventh question asks which operating mode compares one area of a component with another. The answer is the differential mode, where two or more coils compare adjacent regions and respond only to differences between them. These questions summarize many of the concepts that frequently appear in certification examinations. If you can confidently explain the reasoning behind each answer, not simply recall it, you've developed a solid understanding of electromagnetic testing fundamentals. The complete set of review questions and answer key can be found in the source chapter for additional practice. Now let's conclude this chapter and prepare for the next stage of your NDT learning journey. Congratulations on completing Chapter 4 on electromagnetic testing. Throughout this chapter, we've built a comprehensive understanding of one of the most widely used non-destructive testing methods for electrically conductive materials. We began by introducing the three primary electromagnetic testing techniques and then explored the scientific principles established by pioneers such as Oersted, Faraday, Lenz, and Maxwell. From there, we examined how eddy currents are generated, how impedance changes occur, and how material properties influence inspection results. We also discussed probe selection, instrument configurations, inspection parameters, signal interpretation, and the wide range of industrial applications for eddy current testing. Most importantly, we've seen that successful eddy current inspection is not simply about operating an instrument. It requires an understanding of electromagnetic theory, careful calibration, proper parameter selection, and accurate interpretation of inspection signals. Whether you're preparing for certification or applying these techniques in the field, the concepts covered in this chapter provide the foundation for competent and reliable electromagnetic inspection. Thank you for joining this lesson, and I look forward to seeing you in the next chapter as we continue expanding your knowledge of non-destructive testing methods.